Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 2 minutes, this video explains how to construct confidence interval estimates for population standard deviations when the standard deviation is a biased estimator. Let's get started. So, recall from our earlier discussion of biased and unbiased estimators way back when, that the sample variance is the best point estimate of the population variance, because like the sample mean and the sample proportion, sample variance is an unbiased estimator. Well, the sample standard deviation is commonly used as the point estimate for the population standard deviation, even though the standard deviation is a biased estimator. Well, wait. Some of you may be thinking, hold on here. How can this be? How can we be using a bias estimator as our point estimate for the population parameter? Well, here's how it works. We construct the confidence interval for the variance according to this inequality here. And really all we're doing is, if you remember, the definition of the chi-squared statistic was the degrees of freedom times the sample variance divided by the population variance. So if we just swap sides with the chi-squared statistic and the population variance, that's where these values here come from. Of course, we want the upper limit to be greater than the lower limit, so that means the critical values that we put down here on the bottom of our fraction have to be flip-flopped. So the one for the left goes on the right, the one for the right goes on the left. If you think about it, that makes sense. We've got the same number in the numerator on the top of each of our fractions. So the only way that this fraction is going to come out to be bigger than this fraction is if we divide by a smaller number. So the smaller number for the critical value here on the left is going to give us a bigger number. This larger number for the critical value on the right, when we divide that in, it's going to give us a smaller number. And that's what we want. We want the smaller number to be the lower limit and the higher number to be the upper limit. So that's what we do for the variance. Again, notice that they're flip-flopped. The critical value for the left goes on the right. The critical value for the right goes on the left. Now, because standard deviation is the square root of the variance, we can construct a confidence interval for standard deviation according to this inequality here. All we're doing is taking that general form for the variance and taking the square root of everything. And this is how we're able to use a bias estimator as the point estimate for a population parameter. Because what we're doing is going through an unbiased estimator, namely the variance. So by using the variance as a sort of back door, we can actually take a bias estimator that is the standard deviation and use it as the point estimate for the population parameter. So let's review the steps for constructing a confidence interval for variance or standard deviation. First, we're going to verify that the required assumptions are satisfied. First assumption is that the sample must be a simple random sample. Second, the population must be normally distributed. This is a pretty strict requirement. It doesn't matter how large the sample is. We can't use the central limit theorem to come in and say, yeah, if our sample size is over 30, then we can approximate a normal distribution. No. The reason for this, the strictness of this particular requirement, is that the chi-square distribution, which we're using to calculate our confidence interval estimate, is a very skewed distribution. And because of the bias inherent in that skewness, we have to have a population that's normally distributed from the get-go. No approximations here. Next, we find our critical values from the chi-square distribution. We calculate the lower and upper bounds for our confidence interval estimate. And then, if we want a confidence interval in the standard deviation, we've got to take the square root that we calculated for the variance. round the resulting limits per the convention, which is typically using one more decimal place than the original data. Let's look at an example to illustrate this. Suppose we have a group of 22 subjects who took an IQ test during part of a study. Subjects had a standard deviation IQ score of 14.3. So that's the standard deviation of their IQ scores, the 14.3. Assuming the data is normally distributed, construct a 95% confidence interval estimate of the population standard deviation. Well, this is pretty easy to come out. We can find our critical values. That's the first step. We can use software or we can use a table. The tables are okay. They work pretty much the same way as the T and the Z tables that we've looked at already. But I find it's way easier just to use technology. So I'm pretty much sold on the 21st century. I'm going to use StatCrunch. So here are my chi-square calculator in StatCrunch. Notice the numbers that I'm putting in. I've got 21 degrees of freedom because it's one less than the sample size of 22. I've got my confidence level of 95%, which I stick in here. And I'm selecting the between option because I want two tails, one on the left and one on the right. So there's my numbers for my chi-square calculator. Okay, so the number there on the left is going to be that critical value on the left. The number on the right is going to be that critical value on the right. So there are my critical values. Now I can actually construct my confidence interval now that I have my critical values. So I start with that standard form, and I'm going to substitute in for each of those variables what I know. So I've got 21 degrees of freedom. My sample standard deviation is 14.3. And I've got my critical values that I just calculated just a moment ago. So I plug those values in, punch it out on my calculator, and I get 11.0 to 20.4. This then is my confidence interval estimate for the standard deviation. Based on this result, we now know we have 95% confidence that the true value of the standard deviation is somewhere in between 11.0 and 20.4. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.